We can start in 5 minutes. We can let more people come in. Hope that's okay.
Sure. Do you want to just ambiently chat in the meantime about how everything's going? But I mean, how was the IMO this year in such strange circumstances?
Yeah, would the participants like to say in the chat? I think it went pretty well, like given everything was online.
Right.
Yeah, Alejandro says really hard second day.
I was just taking a look at the problems now, and I mean, everyone here is probably a better problem solver than I am, but that certainly seemed the case. I was like, oh boy, um, need more time to think on these.
Did you try at the Olympiads back in your school days?
So I guess yes and no. I was only really like introduced to contest math kind of late in the high school scheme of things. And so I did like the AMC 12 and the AME, and then didn't do well enough on the AME to go to the USAMO. I was just like a couple points off, and it killed me back then. So I was like, oh, if only I had started younger. But I like looking at the problems these days. And it's just, I think, like a shockingly good reservoir of great problem solving examples. Independent of if you're participating in the contests or not. So
Yeah, your windmill question, I think, was at used at a training camp this year at Latvia.
oh yeah, yeah, that's cool.
So do you think you're going to make a video on any of this year's problems?
If I did, I was from the ones I was looking at, problem 3, I was like, ooh, well, that's a nice one. And I was kind of noodling on that. I don't know how other people were thinking about it, but at least it seemed like there were a couple different angles that are quite pretty, could be made nice and visual. But honestly, maybe if I thought more about the other ones, they would like shine through and in just as nice a way.
Yeah, P3 was nice, according to the contestants as well. That sounds good.
I mean, there's sort of like two categories of these contest problems, it seems. There's the ones where, you know, you've got a setup that's mildly contrived, but the contrivedness gives you some like nice insight to go into. And then other ones that just feel pure, like there were as few choices made as possible by like the writer of the problem. They just took some scenario, and that one felt like it felt more pure than some of the others in that same way. I don't know if others would agree.
Yeah, that makes sense. Like if the statement of the theorem is really long, you lose interest halfway through, I guess. Even when generally doing maths, the simpler the statement, the nicer it feels. So, but I'm excited if an IMO problem comes up on 3B1 round soon. That'll be nice.
Yeah, I mean, I think I've only done like 2 or 3 contest math type things, like a Putnam problem, an IMO problem, and people seem to really love them. So the smart thing to do would be to just like lean into that a little bit more, because obviously there's demand, and obviously people, it's not just a matter of them like watching it, they seem to really resonate and enjoy learning about problem solving.
So I've always wondered, is this like your normal voice, or is this a voice you put on for presentation?
No,
So
I just that would, like how I'm like right now.
yeah, because okay, your videos have had such an influence on me that I think when I'm regularly reading my textbooks, it's probably in your voice.
Oh, that's weird. Oh no, I guess I'm flattered. No, I definitely don't put on any kind of voice. That would just seem exhausting. Like every time you go there to record, you're like, oh, okay, well, we'll get into the proper math speaking voice. I'm not even sure what it would entail. But yeah, I don't know.
It's good. The way you explain things is amazing. Well, I think we can start now, I guess. There are
Sure.
over 60 participants, and this is being recorded.
Okay.
So hello, everyone. Thank you very much for being here. And today we have with us Sanderson, also known as 3 Blue 1 Brown, and doesn't really need an introduction. He's a mathematical YouTuber with over 3 million subscribers. He describes his goal as creating content where explanations are driven by animations and difficult problems are made simple with changes in perspective. The use of slick animations, mostly created using a Python library called Manim, mathematical animation, of his own creation. They offer clear and aesthetically pleasing illustration to support his explanations. His videos cover a broad range of mathematical topics, including an exploration of the 2011 IMO question 2 wind wheel problem, which currently has over 3 million views. So today, Grant will be giving a director's cut on his video called Who Cares About Topology, which deals with the inscribed rectangle problem. If you have any questions, please put them in the chat and we'll take, should I interrupt you during the explanation or should we get all the questions in the end?
Please interrupt away. I mean, it's much more fun if things are interactive.
Okay, that's great. So please put your questions in the chat and we'll bring them up. But on that note, thank you very much, Grant, for being here.
Thanks for having me. Yeah, I just want to thank the IMO for inviting me to come, say hello to everyone. I hope the contest went well for you. Let me go ahead and share my screen here. As Parth mentioned, I thought I would just kind of go through one of the videos that I've made in the past that I thought kind of tickles the problem solver's brain in the right way. It's one that I made in 2016 called Who Cares About Topology? And the reason that I think chose this one to just kind of walk through and see if there's questions to talk about, not just the math of it, but also the idea of presenting math, because I think a lot of you in your future will find yourself presenting math in one form or another, it felt like one of those topics that actually shifted my perspective on a whole field. Because when I was a student and high schooler, we would occasionally go to these things like math circles events where people would tell you about what mathematicians do, right? And whenever they got to topology, you might have them talk about these strange sorts of shapes with this kind of rubber sheet geometry. So one example would be a Mobius strip, where they say you take a strip and then you apply a twist and then you glue the two ends together. And then we kind of gawk at this shape and we're like, ooh, it's got one side to it. That's kind of interesting. If you try to assign a vector field to it in some way where you're walking around, it somehow feels different than other surfaces because as you walk around, things might get flipped. And there's this sort of feeling that it's a fun thing to look at and think about, but it was very unclear to me how that's actually math, how gawking at this sort of rubber sheet geometry helps you solve problems, or when we're thinking about a torus as being different from a sphere, is that a problem solving tool, or is this more like people going out studying a wild creature and just cataloging information about this wild creature? So the first time that there was ever a flip where I was like, oh, wow, this can actually be used for problems, was in seeing this really beautiful proof of the inscribed rectangle theorem. So just as some background here, there's this unsolved problem, currently unsolved, called the inscribed square problem, where if you draw any closed continuous loop, the question is, are you always going to be able to find 4 points somewhere on that loop that constitute a square? Now, a lot of progress has been made on this, most notably if you have any smooth curve, where it's basically anything that you would naturally draw. It's like piecewise differentiable. We know that you can always find a square. But as you loosen that and you say, what about even crazier things like fractal curves or stuff where we don't have good information about the slope as you zoom in closer and closer? That's actually unknown. And with any kind of problem solving, you start by maybe thinking of some of the simpler cases to see if you can get a foothold in it. And in this case, if you think of particularly simple shapes like a circle, say, okay, most certainly I can find some kind of square in that. In fact, there's quite a few squares, so that might be a little too simple. But even if you take just a slight extension away from that, it already feels quite constrained, because if we go to something like an ellipse, yes, you can certainly find a square, but somehow it feels like you've been locked into just one particular square. And as you start to say, well, man, if something as simple as an ellipse has such a locking feel, then any particular crazy curve, drawing the boundary of pi, or whatever you might have, how can you find a systematic way to zero in on a square? And the key insight for solving not this, but kind of a variant of it, is to not necessarily target a systematic way to find the particular points, but instead have just an existence proof, something that says there must exist such a thing by virtue of properties of other pieces of math. So the simpler variant is to, instead of asking for a square, see is there any time that we can find a rectangle? So, okay, it's like a square, you've got kind of one fewer degree of freedom, so to speak. And in this case, by leveraging a little bit of clever topology, there's just an utterly beautiful proof. It's kind of, I guess, famous in topological circles at this point. And the first step here is to think about not finding 4 points that constitute a rectangle, but reframing it where we're going to be thinking in terms of pairs of points. So if you say, can we find 2 distinct pairs of points where those pairs share a midpoint and each pair is the same distance apart, that's actually the same thing as finding a rectangle. And sometimes when if I'll like give talks and I'm mentioning this particular video, I like to frame it in terms of you want to describe your math as a sort of story. And in this context, the story itself has an arc of like a fairy tale or a romance of kinds, where rather than thinking of literal characters as like humans in the world, you can think of the problem as a kind of character. Like the inscribed rectangle problem is an entity that we want to get to know. The Mobius strip is going to be an entity we want to get to know. And as you're thinking of presenting your math, really thinking of these as characters that you develop where you're trying to build relationships between them in the same way that pulls you through like a fiction book. I think that can sometimes be helpful for making math feel a little bit less dry. And in this context, like asking about a different framing for the problem where we're getting 2 different pairs of points to coincide in the right way. It's character development. You're getting to know the princess of the story from like a slightly different angle. What is she all about? What's her deeper personality? And it's like aspects of that personality, so to speak, that are going to mesh well to make for like a romance by the end. But in this case, like there's something very very systematic that we can start to do here, because we say, okay, if finding a rectangle is the same thing as saying we want pairs of points to share a midpoint and to also share a distance apart, that's effectively 3 dimensions worth of information that we're associating with each pair of points. Right? With each one, we've got 2 numbers to describe where is its midpoint, and then a 3rd number to describe the distance apart. And if you're thinking in that way, a natural thing to do would be to define a kind of mapping where you say, for each one of these pairs of points, can we take those 3 numbers, the coordinates for its midpoint and their distance apart, and just look at them in 3D space, and what's that going to look like? So to be clear about what I mean here, if we imagine our closed curve as sitting, let's say, on the XY plane, and we choose a particular pair of points, so maybe these 2 pink dots here, I'm going to draw where the midpoint is, and that defines the XY coordinates of a certain mapping. And then the distance apart, we're sort of moving into 3 dimensions. So here I can playfully animate it, where we take that same distance apart and let that now be a Z coordinate. And what this gives us is an association between all pairs of points on the loop and individual points in 3D space. And you all know exactly what you would want to do here. You say, what does this look like if we do it for every single possible pair of points? So not just this one particular that I did. And if you do that, you end up getting quite a pretty shape. It's like a strange architectural design or a Sydney Opera House kind of thing. And to be abundantly clear here, this surface is not a graph. It's not saying a function has an input on the 2D plane and a single number output. Instead, we're looking at the output of a more complicated kind of mapping that takes in pairs of points on the loop and then outputs individual points in 3D space. By the way, the software that I was using to make this particular illustration and a lot of the 3D stuff from this video, it wasn't the usual Manum library that I'll use for other videos. This is just something called Grapher, which is built into your, if you use a Mac, it's just built right in there. And it's actually a very wonderful thing to play with and surprisingly versatile and powerful. And it's an interesting puzzle if you want to think, how do you specifically encode what you need to draw this surface, right? How do you, if you're just using functions and parametric surfaces, take in a closed loop and then output this relevant surface? So that was just like a fun meta puzzle while making the thing itself. And when I read the proof, it describes, oh, there exists some kind of surface above the XY plane, but it didn't draw it. And so the act of actually drawing it somehow felt like it was shedding a different light on the problem that made me engage with it in a way that I hadn't before. So one of the values of trying to add visuals to what you're doing for the sake of explaining is it forces you to concretize things in a way that sometimes builds your own understanding. All right, so we have some writing on the screen here. This will be a fun means of communicating back and forth to just add little subtle notes for how the presentation is going. So one fun thing you can kind of do here is you say, there's lots of different possible surfaces that'll emerge that correspond to each one of the curves, each one of the closed curves that we might do. But in principle, each closed curve has one of these surfaces living on top of it. This way of encoding the midpoint and distance information for all pairs of points. So our goal now is to, in a sense, show that this surface intersects itself. And what I mean by that is to say that we could find two distinct inputs of the mapping, two distinct pairs of points that go to the same 3D output, because that means they have the same midpoint and the same distance apart. So if we can have some kind of relationship with the nature of this surface and show that this property has to hold, that in some sense it intersects with itself, and we'll have to formalize what we mean by that, that actually solves the inscribed rectangle problem, if we know that that's true for any closed curve. So to go about that, well, actually, no, before we go about that, there's one point that I want to emphasize, which is to think about what happens for points that look like x comma x, where the pair of points is really the same point. And in that context, because the midpoint is coincident with x and the distance is 0, that output will live on the curve itself. So this is an important thing to remember for where things are going, that pairs of points which are really two copies of the same point map onto the curve itself. And sometimes when I'll present this in the context of paralleling with storytelling, I'll mention, like, there's this idea in fiction that the author Chekhov mentioned, which is, he said, if in Act 1 you have a rifle hanging on the wall, you had better make sure that the rifle goes off in Act 2 or 3. And what he meant by that was, in his context, never include information in your stories that's not relevant. Now that comes naturally to anyone presenting math. They always like get it down to just the essentials. But there's an implicit point that I think he's making there, which is, if you have a rifle that's going to go off in Act 2, don't just introduce it in Act 2, but also let yourself introduce it earlier so that the audience's mind kind of has it there as a background character. So in this context, the fact that this maps onto the curve itself won't be relevant for a little bit, but I do think there was something nice about inserting that fact much earlier in the story so that the viewer's mind can kind of mull over and kind of wonder, why would that be significant? Like, why would I need to think about that? And it maybe helps for the idea of rediscovery. As you're just about to get to the culminating point, someone has more of a room to feel like they found it themselves, or they were in a position to find it themselves. All right, but anyway, we've got this surface. We're trying to understand this surface. And we're thinking of characters, we're thinking of relationships. So in this context, we're going to take this idea of pairs of points, and we're just going to associate it with something else, like associate it with some other piece of geometry so that we can get a relationship at play. And one thing you might do is basically label all of the points with some kind of number, have some kind of mapping from the curve to the unit interval. This is just another way of saying we're parametrizing it. And when we do this, a thing to keep in mind is it's effectively like we're snipping the curve at some point, because whatever number we start at, associate with 0, that is also going to be what we associate with 1 so that we come back to the end. And doing an association like this feels, it feels a little bit weird because it feels like we're losing all of the geometric information, and the problem is about geometry, positions, and distances. So it would be strange for this to help us make progress, but this is kind of the spirit of topology, is that sometimes you don't care about the specific distance information, but instead you just care about the notion of closeness between points. But if we do care about that notion, we need to remember that 0 is the same thing as 1. Whatever 0 maps to is the same thing that 1 maps to. That might seem like a strange point worth emphasizing when we're just putting it on one dimension. But the whole point here is that when we go into associating pairs of points with something, pairs of numbers that are each between 0 and 1, we might think of with Cartesian coordinates, sitting somewhere in the unit square where the x coordinate is between 0 and 1, and the y coordinate is between 0 and 1. But if we want to remember that these coordinates are referring to points of the loop, we have to remember that 0 is the same thing as 1. So everything where the x coordinate is 0 needs to get glued to everything where the x coordinate is 1. And I've drawn arrows to indicate how that gluing would happen. And then same deal for y coordinate 0, y coordinate 1. Maybe a lot of you have seen this idea here, but just to kind of reiterate, it's that if you have a given number, like 0.2, that corresponds to a position on the curve, we're associating pair of numbers, which is to say pair of points, with one of the points of this square. But when you do that gluing, which is to say you remember the cuts that you had, what we're saying is that the set of all pairs of points on the loop has the shape of a torus, so to speak. And more concretely, what we mean by that is that there's a mapping between the two, so that if you make tiny little nudges to one, you slightly tweak what pair of points you're talking about, it only corresponds to tiny little nudges on the donut. And with sufficient epsilons and deltas, you can make that as rigorous as you want. In topology, they just have a notion of open sets that also captures this idea of small wiggles in the input only correspond to small wiggles in the output. But the idea is that the relationship between pairs of points on the loop and this torus is exactly the same thing as the relationship between pairs of numbers and the xy plane. It's a way of giving a spatial interpretation to tuples of things. But this isn't quite the shape that we want, because if you think about it, when you change the order of the points, 0.2 and 0.3, instead 0.3, 0.2, these will look like different points. They're different points of the torus. But why are we doing any of this in the first place? We're trying to associate, we're trying to find two distinct pairs of points that have the same midpoint and distance apart. But if I tell you, hey, I'm considering the points AB as a pair to be distinct from BA, well, then you'd say, okay, I found two distinct pairs of points where they have the same midpoint and same distance apart. You just swap the two. And okay, I guess that's a rectangle if we want to consider the degenerate rectangle, but clearly that's not the spirit of the question. So to capture the idea of genuinely distinct points, the ones we want to consider distinct so as to find a rectangle, what we have to do is acknowledge that any point that looks like xy should be considered the same as a point that looks like yx, which is effectively one more gluing procedure. But in this case, the motivation of the gluing isn't just that we're playing around with like construction paper and looking at strange shapes. The motivation is that we're trying to encapsulate the idea of unordered pairs of points in some kind of other mathematical context. And we're trying to do it to actually solve a problem. We're not just playing around. Now in this case, in order to make that association, we essentially fold over the unit square like a grilled cheese sandwich, okay? And as we do this, one more time, I would like to draw your attention to that rifle that's hanging on the wall, which is what happens to the points that look like x comma x, that are really the same point listed twice. They all live on the crease of that fold. And I'm going to go ahead and color that crease red, just so we can keep it in mind. And again, by inserting this little fact a little bit earlier, maybe in the viewer's mind or whoever's consuming the proof, they start to think, oh, why would that be relevant? What's going to be the relationship between the crease of this fold and the curve sitting on the XY plane from our Sydney Opera House view before? And as you mull that over, we'll just kind of move forward with the more pressing question, which is, how do we glue those arrows back together? Because after the grilled cheese fold, it looks a little bit strange. And as you start to think about it, you say, okay, we've got points, let's say on the left of that bottom side, need to be associated with points on the bottom of the right side, and points on the right of the bottom side need to get associated with points towards the top of the right side. And it feels like somehow this just isn't quite possible, just the way that the arrows are. If you try to twist it, it's not going to work. But there's a clever trick we can do here where we take a step backwards before we go forwards. And we say, I'm going to cut those apart so that the arrows, the purple arrows we need to glue, are prepared for the gluing. And I just need to remember the cut that I made so I can glue that back together later. Because all we care about is, if we make this split, just remember that those points should really be considered the same. And when we do that, we can glue those purple arrows together fine. That's what corresponded with, the zeros being equal to 1 from our original mapping. And then to repair the one cut that we made, we have a strip where we need to do a twist in order to do that gluing, which means the proper shape, so to speak, that encapsulates the geometry, not even the geometry, the topology of unordered pairs of points is a Mobius strip. Now that particular move where you have this clever cutting argument, I think was one of the most pleasing things I can remember seeing back when I first saw this. Was this just really lovely way to inexorably find yourself with a mapping between unordered pairs of points and the Mobius strip. And again, more concretely, what we mean by a continuous one-to-one mapping that gives the idea that these are really the same shape, so to speak, is that if you were to slightly tweak the unordered pair of points that you care about, just jiggle them a little bit, it only corresponds to a small jiggling on the Mobius strip. And if you wanted to confine the amount of jiggling on a Mobius strip, you can always confine the amount of jiggling in the initial space as much as you want, which is a way of just capturing the idea that there's no tears that take place. There's no sudden jumps in our mapping. So what we have here is saying, okay, Mobius strip points are effectively the same as unordered pairs on the loop, but we also have this mapping from unordered pairs of loop on the loop to this surface that sits above the XY plane. And what that means is that surface we defined earlier is in effect a mapping from the Mobius strip into three-dimensional space. And the thing that we're trying to show, the thing that we need in order to know that the inscribed rectangle problem is true, is that there's a collision, that as we do this mapping, there's going to be two distinct pairs of points from the Mobius strip that land at the same point in three-dimensional space. And I'll just show you what that mapping literally looks like in this context, which again, it's a fun puzzle to think of how to actually encode that using parametric surfaces and concretize it in some way. But as we do that, this is what it would look like for the Mobius strip that corresponds to unordered pairs mapping onto the relevant surface. And as we do that, notice what happens to the red boundary of that Mobius strip, which was the crease of our original fold that corresponds to pairs that look like XX. We know that those have to end up on the closed curve itself, because that's what also corresponds to pairs that look like X comma X. So we have this sort of strange thing happening where that red line that has this twist associated with it needs to get flattened out onto the XY plane, and the remainder of the surface needs to end up entirely above the XY plane. Now, at this point, at least as I made the original video, this is where any pretense of formality stopped, because essentially said, if you play around with the thought of a Mobius strip in your mind, you may be able to convince yourself that there's no way to do this without that surface somehow crossing into itself. For a lot of you, I imagine that's not a satisfying answer because you want to know a nice rigorous proof for it. But I think the desire for that rigorous proof of saying, okay, yes, intuitively, it feels like I can't take a Mobius strip, put its boundary onto the XY plane while the interior is entirely above it without forcing it to cross itself. There's no one-to-one way to do that. In order to prove that, you're going to need to develop some of the other tools of topology. One way could be if you define this other type of surface known as a projective plane and the relationship that has with a Mobius strip and whether you can embed it in 3 dimensions, but that's already a little bit of heavy machinery. Another way is you can start maybe thinking about winding numbers, and you can think about orientability. I'm going to leave it open here just because I only wanted to talk for a little bit of time. But the idea is that almost all of the proof, you have the substance for it at this point. And the thing that you're presumably itching for, if you want that last rigorous step, involves substantive questions about topology in the way that mathematicians care about. And it's not just in a gawking at rubber sheet geometry saying, oh, is a coffee mug the same thing as a donut? Instead, there's a real motive for trying to define some of these terms. And I think that sometimes is lacking in an undergrad education. This idea of why we're defining the things that we are, like why do we care if a certain surface can be embedded in 3 dimensions, or why do we care if we've got this notion of orientability and not? And this was the first time that for me, I felt like, yes, I do care. I now see how this Mobius strip can be used to solve problems, to encode information about other things. Just if you're curious, I illustrated for this particular mapping, which there's many different, but a particular pair of points that do end up landing on top of each other, which is in a sense a way to see the rectangle that lives inside the curve. It's just through a certain other chain of consequences. I thought I would also share, just even though that this was maybe, I don't know, a 17 or 18 minute video that I made, the original place, this isn't from the original paper, the original place that I stumbled on it, encapsulated the entire substance of that proof into a paragraph, which is very dense. And I'm sure many of you who just spent a couple days writing, proofs for up to 6 problems in probably a way that was more concise than the amount of time that is required to think about it might appreciate just what that mapping looks like. So, he mentions how this mathematician Vaughan has found a particular proof, and as he phrases it, he says, let M be the set of all pairs x, y, where x and y are parts of this closed curve, and define this mapping F that goes from our set M into R3, essentially by letting the first 2 coordinates, F1 and F2, be the midpoint. And then the third coordinate is the distance between them, so the thing that we just saw. Then he says, now M is a Mobius strip, which is 5 words that actually carry quite a bit of weight, that if you didn't know this association before, that's not at all an obvious statement. But if he's speaking to mathematicians, then it's just kind of this common knowledge, unordered pairs have the shape of a Mobius strip. And if S does not contain the vertices of a rectangle, F is 1 to 1. Again, a rather dense sentence, but kind of beautiful in its own way. So then f of m is a Mobius strip which lies in the closed half plane z greater than 0. So the interior is entirely above the plane, and it meets z equals 0 on its boundary S. Again, a lot of density there for thinking through why it meets the why the boundary of S meets z equals 0. But that's kind of how math is often written. And then his reference to like what formalizes that is to make mention of this thing called a projective plane. And my point in mentioning this is just that as you find yourself consuming math, sometimes recognize that in the density of textbook pages and papers and things like that, sometimes you can have a very beautiful storyline that's worth sharing with others or your friends or whomever you want, that is just this hidden gem inside some of the density there. And so let yourself take the moment to really mull over what seems like a small percentage of a text and see what you can extract from that. And don't just let yourself plow through it as quickly as you can with the hope of consuming as much in as little time as possible. And the final thing to mention is that there's actually been progress on things related to the inscribed rectangle problem just this year. There was a very nice Quanta article about it that if any of you follow the magazine Quanta, where essentially they showed that for smooth curves, so the kind of the easier case where we know the inscribed square problem is true, it's not just true that you can find an inscribed square, but you can find inscribed rectangles of every possible aspect ratio. And to give a little intuition for why smooth curves make this a notably, I'm not going to say easier, but a more tractable problem than rough curves like fractals, is if you look back to what we're doing, we're associating pairs of points with, like I said, 3 dimensions worth of information, 2 for the midpoint and then 1 for the distance apart. The only other parameter that you would need to describe the aspect ratio of this rectangle, how squished is it a square, is to describe the angle of that particular line or the slope of that line. And in this case, what really mattered was to be able to control what happened as we approached pairs that looked really close together towards that boundary. That's the thing that you lose control over if you don't have smooth curves. But if you do, you can leverage that. And the nature of the proof that these two wrote for this more general form of the inscribed rectangle problem looked and felt very similar. Instead of mapping into 3 dimensions, you're mapping into 4 dimensions, where that 4th dimension describes the angle between them. And then you're starting to ask questions about the nature of mapping Mobius strips into 4 dimensions with all of the constraints implied by this problem. So I think that's just fun food for thought to mull over and to recognize just how recent some of this stuff actually is, that it was happening this year. So with that, I think I'll go ahead and stop the screen share and just answer questions or chat with people about how their IMOing is going and things like that, and hand it back over to Parth.
Thank you very much. That was a wonderful talk. So please put your questions in the chat and we'll be happy to answer them. But so Samuel asks, what's your favorite area of maths?
Oh, favorite questions are always hard because you're always going to point to something that you were thinking about most recently. I would say it used to be like number theory type things, I think is what like encapsulated my attention most readily. But honestly, as time has gone on, I don't like have a particular favorite. There's just so many different things. I really love computer science and a lot of the things that happen there, like especially in information theory. I never learned that much physics in college, but I've been learning a lot more recently. And, of course, the flavors of math associated with that are very different from like number theory or information theory stuff. So it really runs the gamut. But yeah, favorite questions are always hard. So I'll maybe just say like those broad categories seem to be what I enjoy a lot.
So what makes a good question in your opinion? How do you choose your video problems?
So I love something where you mentioned this in your intro that I must have written somewhere, where a shift in perspective is what makes a problem go from really hard to tractable. Not all problems have this characteristic. Sometimes it's really just you're systematically plowing through what needs to be plowed through. But there's a category of problems or ideas in math where seeing an association between things that don't initially seem associated, or changing how you're viewing like a probability question as instead of sampling from one distribution, sampling from another that turns out to be equivalent. Or in this context where instead of thinking of rectangles, we're thinking of pairs of points, and that can be thought of as a Mobius strip. Like all of that shift in perspective, making something easy, that's really what tickles me the most, and I think is what I try to share with the channel, which is not to say that's the full extent of math or what makes it beautiful, but that's the niche that I think I've tried to zero in on.
Okay. So there's a question by Haik Tarkanian, and Haik says, there's a point of view backed by research that videos where explanations are very clear and not much effort from the brain can lead you to have a fake feeling of understanding, or they just don't stick for long. So what's your opinion about that? And should one make some confusing statements in the video so that the viewer really understands the topic or not?
Yeah, well, I think that's true, actually, that this idea of giving someone the illusion of understanding through clarity happens, and that it doesn't correspond to actual understanding. What I would say is, I think the benefit actually heavily outweighs whatever cost there is, because the main goal in a lot of this stuff is to make people self-identify as loving math, which most people don't. And even a lot of the audience of the channel, even though clearly it's people who probably already like math who are watching about it on YouTube. I know for a fact a lot of them aren't, they're not IMO participants, they're not people who usually nerd out about math. So first getting someone to the point where they think, I can understand this, or I can find it beautiful, that I think is then what leads you to doing things like actually solving problems or doing more of the hard work stuff that otherwise feels very unmotivated. But to the point about deliberately putting in points of confusion, I think my instinct is that the way to combat this like illusion of understanding is less a matter of being purposefully confusing, but is more trying to elicit things from the audience in one form or another. So taking that moment to pause and just like really actively encourage someone to think about it, which 90% of people won't do, but who cares? It's that 10% who are willing to be active that are who you care about. And taking more of an opportunity to let people have information flow from within their brain to outside rather than vice versa, is maybe how you can try to make lectures more effective. On the whole, though, lectures, their role shouldn't be thought of as the be all and end all. Like where learning actually happens is in solving problems, and maybe we shouldn't even pretend that the learning is happening in the lecture, and that it instead serves as like a point of clarifying, priming people, and inspiring people to do that second phase. Yeah.
Okay. So there was a question on the sheet that says, what's the most memorable maths problem that you have solved?
Oh, I don't know. Yeah, that's an interesting question. I guess like I think there's an unappreciated category of problems. Like you've got academic research, which is shooting for problems that no one has ever solved. Like it's at the boundary of understanding. You've got teaching, which is aimed at taking the things that we understand, but like teaching them to individuals who don't yet understand it. But I think there's this category of things that like we don't yet know how to explain. Like there's this paper by Timothy Chow about a thing in set theory called like the forcing, that's just like famously confusing. And in the beginning of it, he said, I believe that this is an unsolved expository problem. And this paper is an attempt to make partial progress towards that. And I loved the framing that there even exists something called like an unsolved expository problem. So the things, and this is heavily biased by the fact that like what I do is make videos and I'm not an academic researcher. The things that I look back and feel like proud for like solving in some sense, it's never something that like wasn't known before, but it's like a different way to go about explaining what might otherwise have been seen as like a hard problem. And it might be it's hard to remember exactly, but one that I remember feeling like enjoying how I did it was a video about the Leibniz sum, where you take 1 minus a third plus a fifth minus a seventh. You oscillate reciprocals of odd numbers like that, and it converges to pi fourths. And really trying to show like how that connects to a circle and to justify some of the number theory that goes into it. While it's hard to point to any like one particular thing that was like, this was the original insight, somehow if I was like contrasting the final result there with the just like the texts or others that had like explained that particular sum, it felt somehow like progressed towards making a certain set of things more understandable to a broader audience. Yeah.
Okay. So, what motivated the shift from actually thinking about academic problems and research to explaining problems?
I mean, that's probably a personality thing. I mean, I mentioned that I really love computer science as well as math. And I think one thing that's neat there is, like, if you think, like, what is computer science? It's effectively turning math into physics, right? It's taking things that are math, but then making them a thing that is true in the world that's physically happening. Whereas physics does the opposite. It takes things that are physically happening and like turns them into math. Um, and what I think that means is that you have a really interesting opportunity to like turn otherwise abstract concepts into something real that people can look at. And the idea of finding this intersection between like programming and animation is effectively a way of like you turn the math into a program that turns it into an animation that hopefully then turns it into understanding for someone. I think that like cycle of things is something that had like excited me for a while. And there's not a role for that in academia or research in the same way. And uh, I'll be like totally candid about something. I think a regret that I have from my undergrad was not engaging with the faculty at my university as much. And I wouldn't be surprised if had I gone back in time and like actually built that relationship with potential like mentor mathematicians, maybe I would have been more readily steered towards like the normal track for like mathematician, for better or for worse. And so to those in the audience who like will soon find yourself at a university and like maybe thinking about becoming an academic mathematician, like by far the most important thing that you can do is build good relationships with the faculty and potential mentors during your time there. Much more so than like that has much more importance than time spent on classes. And so maybe like the most like self-critically honest answer to the question for why I went one direction versus the other is like a sort of fault through my undergrad of not actually engaging in that way that that would have best primed me for a usual academic path.
Okay. Are there more questions in the chat? What is the status on your probabilities of probabilities series?
Oh yeah, I'm actively writing the third one right now. I am. It's funny. I was like started this thing. It was supposed to be one video. Then I was like, oh, I'll make it two, and then it was going to be three. But then before the third one, there's like the whole lockdown stuff, and I decided to do this collaborative lockdown math, like live lecture series with some friends. I did it some time, and then some other like collaborations that I had on the calendar for a while before had been coming up. Like, oh, I'll finish this collaboration with like Matt Parker. I'll like do this one with Ben Heater. And then by the time I realized, I'm like, oh wow, it's somehow been like half a year since I went from like part two of something to part three. Sorry about that, everyone. But that's just sometimes how it goes. Also, for whatever reason, I find probability harder to write about than other topics. It's not that it's a more complicated topic. It's just that it's harder to know. There's so many different potential audience members for like where are they coming in from. And I think the way that you talk about it to like a math student is very different from the way you talk about it to like an engineer or to like a physics person. And that difference in where people are coming from sometimes makes it a little bit more challenging to decide like what angle you want to take.
Okay. So what's the origin of the name 3 Blue 1 Brown?
Oh, it's a little embarrassing. So when I originally made the channel, I was like, I wanted to make the logo like a loose depiction of my right eye color, which is it's 3/4 blue and 1/4 brown. So it's like this slightly genetically unique thing. I'm like, oh, it's a channel about like seeing math, and it's like a genetic signature I can put on it, the same way you might make a channel name, just your own name. And I wanted the name to be a little weird. So, it's like, there's nothing else in the world that the phrase 3 blue 1 brown could possibly mean. Whereas if I called it like fun math or like math insights, like there's a billion things that could point to. So the combination of the strange thought for what the logo should be and like wanting the name to be weird. Yeah, that's kind of where it came from.
So what do you think could be improved in the current state of how maths is being taught in schools and colleges?
Great question. Okay, so one, I think de-emphasize the importance of lectures on learning, kind of what we were talking about before. I think the role of a lecture should be when someone is at that phase where they actively want to understand a new thing, and we can talk about what gets them to that phase, then they have access to the lecture to do that. And I think this is what recording lectures or having things online, that's where the value really comes from, is if you have a wide catalog of like the best possible explainer of a given topic, you can like find it on YouTube or wherever. Then you can do something where most of the class is oriented around like problems and projects, and that as the student is like progressing through their project and hits a point of, I can't proceed because I don't understand a particular piece of math, then they can get pointed to it. And it doesn't have to come at a particular time in their, in the school year, you know, rather than the trig student in high school saying, it's now week 5, we're going to learn about the tangent function. Maybe they don't care about the tangent function. Instead, if they're actively programming some little game where they've got a cannon that needs to like shoot something, and they need to associate the angle with the slope of that line, at that point they're like, oh man, like, well, how do I do, what function do I call? And at that point, you know, the mentor or the teacher, whoever else, can come right and say, I'm so glad that you asked. Like, what you want to learn about is the tangent function. And then they point them to not their own lecture of it, maybe if theirs is the best, but like somewhere online, there's going to be like the best explanation of the tangent for that student. And it seems a little weird to have every trig teacher in the world redo the work of doing a lecture on that topic, when by definition, the vast majority of them won't be doing the best lecture, although they might be like quite good. And effectively, this falls under the umbrella of like flipped classroom models. And it's something that's been talked about a lot for the last probably 10 to like 15 years. But as more and more content gets put online and is recorded, and as we learn more about the kinds of projects and problems that make for the most learning, I think making attempts to shift in that direction and learn from the successes and mistakes of past flipped classrooms like just makes more and more sense.
Right. So a question asks, what's your go-to example of beautiful maths to convince people that maths is awesome?
Depends on the level. I think if it's, yeah, so I made a video about it because naturally I think it's like something that a lot of people would like. I'll make a video. One thing that seems to have pretty universal like appeal, almost independent of where someone's coming from. I have this one about if you take blocks sliding on a frictionless surface, and let's say one of them is of mass like 100 and the other is mass 1, and you have it slide and it hits the mass 1, and then there's a wall and it kind of bounces off that. And there's a set of collisions that take place that it's totally idealized as physics goes, because we say, you know, no energy is lost to friction of the collisions. As the mass of the big block grows by powers of 100, the number of collisions has the same digits as pi. And so that, like, I mean, everyone knows pi, everyone loves pi. And so the idea of seeing it in such a weird and unexpected place, I think that pretty universally like takes people saying like, wow, there's something going on here. And if you know, let's say you run into a skeptic that's like, yeah, but that's nonsense physics, right? As we get some huge mass, this like frictionless stuff and not accounting for gravity and all that, like that wouldn't really happen. And if you want to explain that that's not the point, a fun fact that I had no idea about, but you can connect that idealized physics setup to quantum physics in a way where this block collision setup ends up, like the set of exchanges that happen ends up being mathematically identical to a quantum search algorithm called Grover's algorithm. And the idea is that the same math that you're using to analyze that setup is directly relevant, even if that physics is idealized. Like it's actually directly relevant to something as practical as quantum computing, if you consider that practical. So even to the skeptic who sees it as something that's not true physics or not truly connected to the world, you can come and be like, ah ha ha, but actually it is.
So the people do enjoy beautiful explanations, but I guess even then the popular opinion still stands that maths is just abstract nonsense. I mean, that's what a common person thinks. And where do you think this mentality arises from? And
I'm not entirely convinced that is what most people think. I think a lot of people begrudgingly acknowledge that, like, yeah, all the nerds and engineers that seem to be using math to make magic happen, like, especially in a world dominated by algorithms. I don't know how many people genuinely, like, would say that math isn't useful, but what is definitely the case is as you choose particular beautiful problems, choose anything from the IMO and you tell it to someone, and then, yeah, they'll agree that it's like abstract nonsense. There, I think the key is to give people appreciation of the connectedness between things and say like, yes, of course, this like IMO problem 3 you will never need to like take 4n stones of different colors and like categorize them in the right way. But the tactics being used to solve these problems do have direct mappings onto like computer science and physics. That I think is underappreciated by the general public, like how connected this is. And then is also something that's teachable. Like you can show a number of examples of this kind of connectedness between useless abstract nonsense problems and for whatever reason, I think computer science is often like a little bit easier. Maybe just because I love discrete math a little bit more, but either if you want to go in the computer science or the physics direction, like you can find nice examples of getting those to touch that will convince the average person, I think.
Okay. So in relation to the last question about high school math, what concept or area of math do you think should be taught in high schools, but it isn't because it is too hard?
I mean, okay, I think combinatorics. Uh, it's weird that that's not taught in the same way that algebra and other things are, because I think it teaches you how to organize your thoughts, and that is like generally useful. And it's got applications to probability and such, but really it's the idea of like organizing problems in different ways. That seems, I don't know if the reason it's not taught is because it's too hard or that it seems not as relevant as other things. Linear algebra, I would put in there where it doesn't make sense that we give as much emphasis to calculus as we do in contrast to what's clearly more relevant to a lot of people who go into like variants of engineering. Of course, calculus is important, but like it's almost always the case, the more linear algebra you learn, the better. So might as well start as early as you can in high school. And it's not so hard that like students won't be able to do it. It's just a matter of choosing how you present it the right way. So that would be the biggest one.
Right. So what would be your advice for someone wanting to get started with making maths animations or educational videos?
Sure. So I guess there's two ways of answering it. One is on the like how do you make it, like what software tools to use and things like that, and the other is around what kinds of topics, or on the content side, like how should you think about it. The more important one is on the content side. Like content matters much more than production quality. What a couple things I wish I had like thought about earlier is make sure you have good sound quality and just like take the time to like make it good early on. A lot of my early videos just have terrible sound and I think are more obnoxious to watch because of it. So you can say that's the one aspect of production quality that probably does matter. Then titles and thumbnails are actually important if you want people to watch it. And just taking a little bit of thought on that are the two things I didn't necessarily know early on. In terms of putting together like nice visuals for math, which I can think is important. One, don't be afraid to just like hand draw stuff. If you've got good visuals, you can often get them across very effectively with like a playful drawing. And that might be like the cheapest, fastest way to do it. GeoGebra and Desmos are pretty excellent tools out there that are worth playing with. Mathematica, if you want to do some like programmatic animations. Like I said, the library I use is open source. It takes a little bit to get started with, but I think it's sensible enough. Ironically, it's not great for like graphing stuff. If what you want to do is like graphical, just use Desmos. But if what you want is more like an object-oriented control of all of the objects on your screen and how they might mathematically relate, that's sort of where, like the reason that I made it. What are other tools? So focusing on the content side, try teaching your topics to like actual people before you make the video, just to see what resonates with them and what doesn't. And you'll probably learn a lot about things that you've taken for granted or things that really inspire someone about the problem that you like forgot as an inspirational part. And especially things that are confusing that you forgot were confusing, because this is the thing where once you know a piece of math, it can be really hard to empathize with what it was like not to understand it. So really being cognizant of that fact before you put together a presentation makes a big difference for the viewer's experience.
So where do you come up with the intuitions that you show in your videos?
I mean, I don't know. Like I read a lot of things and then just keep notes on what might be like worth presenting. I mean, a lot of it, it's not like it's just a totally original thing. Usually it's pieced together from what someone else has said, and maybe I want to like put a little bit of an extra spin on it. If it is something that's slightly more original, that's sometimes when you're just like noodling around with a notebook for a while and trying to ask, not just, okay, has the problem been solved, but do you feel like there's been the full like satisfying answer to it? Like this last week, I was thinking about why pi shows up in a Gaussian curve. Like what's an explanation you could give to someone for where the hidden circle there is? And I thought that I had like a nice understanding, like, oh, there's this cute integral trick that you can do where you extend it into 3 dimensions and you've got this like rotational symmetry. But I realized that just sort of feels like a trick that happens to work. And it doesn't necessarily feel like it's giving you insight about what bell curves as a core part of statistics and the way they arise in statistics, what on earth that would have to do with like the rotational symmetry there. And like drilling in a little bit further. So it's like, even if it's proven, like, okay, what is it that is the core defining feature of a bell curve we care about here? And maybe you think of like central limit theorem or aggregating a bunch of samples from some distribution. Okay, what is the core reason that this integral trick work? And you talk about how if you take this e to the negative x squared function and you multiply it by e to the negative y squared, so you like have this independence in 2 dimensions, how that actually has a rotational symmetry to it in a way that most functions don't. Say, what's the connection between those 2 facts? And that I think is like a much more interesting thing to drill in on. So I guess in that way, like being persistent on actually seeing the connections between stuff beyond proof, right? There's rigorous truths and then there's moral truths in math. And like seeking those moral truths, not just is this true, but why should it be true? I think that level of insistence is it's just worth adopting. I think it makes it more fun, and especially for someone who wants to explain this stuff.
Have you tried to do a full IMO? So have you tried to solve an entire IMO paper?
Oh, that's a good question. I guess probably the honest answer is no. The way that I'll consume it is I'll like look through the problems and then I'm like, oh, this seems pretty. I'll try to solve it. But I've never like sat down for 4.5 hours and said like, okay, I'm just gonna like free myself of all distractions and just sit and like write the test, which is maybe I should. Yeah, like clearly I should, but somehow that's just never been the way I've done it.
It would be a fun thing to do.
Yeah, clearly. In fact, oh, I guess it's too late because I've already looked at the 2020 problems, but I'll find, yeah, maybe sometime later today I'll find one I never looked at.
There's a suggestion that says live stream yourself doing it. I would. Nice.
Oh man,
Yes.
high risk. I would record myself doing it and then like maybe edit it down. I don't know if anyone wants to watch 4.5 hours of me being like, wait, where did I put the X again? And just like being actively confused, but yeah, who knows, maybe.
But if you come across unsolved problems, do you just think about it and try to solve it? Like, have you tried to think about the inscribed square problem?
That's a good, I mean, I got a little bit of familiarity with like how it was solved for smooth curves. I guess, I mean, I naturally like thought about it a little bit in a more complicated case, but it's nice to see enough like why it's hard, but then frankly, I don't know the math that's at the forefront of addressing like the non-smooth cases. And maybe that would be like good motivation to like learn it. But part of what ends up happening, I think, with any like career trajectory is you've got like the things that you can focus on and things that you can't. And there ends up being like a lot of questions for like how to spend time. And like I said earlier, I find a little bit more interest in that category of like unsolved expository problems, where maybe it's just like knowing, okay, I'm not going to solve the inscribed square problem. Although I could spend like a bunch of time to try to gain like expertise in like the nuances associated here, but I'm not entirely sure if that would be the best use. But I think like anyone, it's fun to just sort of think about these things, at least enough that you can understand why they're hard. Like I remember spending a lot of time several months ago thinking about odd perfect numbers, just because that's actually quite a fun, just like little puzzle. And you know, getting all these like partial results on how many, like, oh, if it decomposes into primes, this is how many primes there must be. And you can certainly get yourself to the point where like, boy, it would be a crazy coincidence if one of these existed. That's obviously very different from getting to a proof, but I think spending that time is like as fun as it is with anyone else. But I don't have any illusions about like whether I would be the one to solve that kind of stuff.
Most of the comments are just asking you to solve it on solve the IMO paper on stream. People really want.
Okay, all right. I'll do that one. I'll embarrass myself one day and stream some IMO solving. Yeah, that I guarantee that.
So have you ever just decided to make a video on a topic just to get an understanding of it? So I'll teach this topic so I understand it better now.
Yeah, I think neural nets was one where I did that. I was kind of like, this is a nice excuse to try to get a little bit of familiarity with, because I had learned a little bit about them in college, but it had like been a while. I think more often what happens is just like you want to learn about new topics, as I'm sure like all of you do, and you're just like ambiently reading that, kind of with the vague motive that like part of why I'm like learning about this new thing is that maybe it'll be a video at some point. But what I've never done is said like, all right, I'm sitting down, like the next video is going to be about this thing that I don't know anything about yet, and I'm just going to like research and then make it. Because I think sometimes you want to have ambient thoughts about it for like up to a year, where it's just you're collecting notes on like all these different things. And sometimes it's not yet like ready to be a video or ready to be a lecture. Because at some point it's like, well, let the person who actually has like deep thoughts about this be the one to like make a video on it, rather than if I've like learned about it last week, like odds are I'm not capturing like the nuances that someone who had a longer relationship with it would. That could be a channel. I mean, that could be a style you adopt, which is this very frank, like, this will not be the like the full nuanced description of this topic, but if you just want to like watch like me try to learn about something, and there's some other, I mean, there's a number of like channels on YouTube that do things to this effect, which I think is very valuable and honest. But the function that serves is a little bit less that of a traditional lecture, and it's a little bit more like a personality channel to just like watch people do things,
Right.
which is cool. I mean, there's value in that, and could be like fun project.
So I think we'll conclude with, do you have any advice for all the IMO contestants here?
Yeah, okay, so it's kind of something that I referenced a moment ago, but when you're continuing forward in your pursuits of math or whatever else you might be doing, recognize that like the human relationships are going to be the things that make it most. So whether that's as you're a researcher, it's a matter of like who you collaborate with, as your students, like relationship with your mentor, but also just your peers. Like, you know, the beauty of an event like this is it does kind of bring people together. Like each country's team, I'm sure, just has this tight knit bond because they have such shared interests and experiences. And almost more valuable than doing the test is like the set of experiences you have or relationships that you build there. And this is true not just in math, but like everywhere in life. But it's especially because, I mean, the math enthusiasts don't always have the reputation of being the most social and gregarious of students. That's a false like perception sometimes, but that is like a reputation that exists. But making an active effort to violate that like will make your trajectory, whether that's into academia, into engineering, into education, whatever it might be, more successful for almost any definition of success that you have. So yeah, I just would really emphasize that.
On that note, thank you very much, Grant. That's wonderful advice. And thank you very much to all the participants for being with us here. And there were some amazing questions in the chat. Thank you very much.
Thanks for inviting me, and great questions. This I saw we only got to answer like a fraction of them, but like I really appreciate the like interaction and curiosity from everyone. So hopefully I'll see subsets of you at some other parts in life and answer more such questions and ask you some of my own. I'll tune out. Thanks for inviting.